A very good morning to one and all. Myself, D.K.Shareef. I'm a research scholar of Mohan Babu University in the Department of Computer Science and Engineering, School of Computing. Here, I'm presenting my research paper in IJEECS. My paper title is Enhancing Energy Efficiency and Reliability in Wireless Sensor Networks Using BioGAT Optimization. Abstract. The BioGAT model, as proposed, presents a novel methodology for enhancing the efficiency of wireless sensor networks, which are essential elements of contemporary communication and sensing systems. For real-time monitoring and data analysis, wireless sensor networks are comprised of autonomous sensor nodes that are outfitted with processing, wireless communication, and sensing capabilities. These nodes are deployed in a variety of environments. By means of an advanced optimization model, this work aims to address critical challenges in wireless sensor networks, specifically in the areas of node placement, energy efficiency, and network reliability. The BioGAT model, as proposed, presents a novel methodology for enhancing the efficiency of wireless sensor networks, which are essential elements of contemporary communication and sensing systems. For real-time monitoring and data analysis, wireless sensor networks are comprised of autonomous sensor nodes that are outfitted with processing, wireless communication, and sensing capabilities. These nodes are deployed in a variety of environments by means of an advanced optimization model. This works aim to address critical challenges in wireless sensor networks, specifically in the areas of node placement, energy efficiency, and network reliability. Wireless sensor networks have evolved significantly, becoming indispensable tool in fields such as environmental monitoring, healthcare, and industrial automation. These networks, which consist of small, inexpensive sensor networks, allow for real-time data collection and transmission to central base stations or SINs. The evolution of wireless sensor networks reflects the growing demand for timely and accurate information, which drives innovation to meet the needs of contemporary applications. The challenges inherent in wireless sensor networks necessitate ongoing optimization efforts. One of the most significant challenges is the limited energy resources of sensor nodes, which are frequently constrained by battery capacity. Our study suggests an integrated approach that combines biographically based optimization (BBO) and graph attention networks (GATs) within wireless sensor networks. BBO provides a mechanism for selecting optimal cluster heads while balancing energy consumption and network coverage. Meanwhile, GATs allow for adaptive network topology changes in response to dynamic events such as node failures or energy depletion. By combining these methodologies, we hope to improve wireless sensor network efficiency, robustness, and sustainability in a variety of operational scenarios. Our primary contribution is the development and application of the BioGAT model, which combines BBO and GAT methodologies for wireless sensor networks optimization. My related work. Yadav proposed a new congestion avoidance strategy called ECAHA, which combines Hoffman coding algorithm with ant colony optimization. This novel approach aims to efficiently reduce network congestion. The Hoffman method has one limitation. It requires prior knowledge of the probability distribution of symbols in the data stream. This can be difficult in dynamic or unpredictable environments where the distribution may change dramatically over time. Zolan present an innovative centralized cluster tree-based routing system with a mobile sync. This system is intended to improve network routing efficiency by grouping nodes into clusters and employing a hierarchical routing structure. Lilhore use a genetic algorithm and a data fusion technique to solve a specific problem. Genetic algorithms are a powerful optimization tools that is widely used in various fields. Who developed a new routing protocol called EHR, Energy Harvesting Routing, for energy harvesting wireless sensor networks. In such networks, their protocol aims to optimize energy consumption while also maximizing network lifetime. In order to improve the longevity and efficiency of energy harvesting wireless sensor networks, Tang Zhang and Xiang introduced a routing protocol that draws inspiration from Pfizer, my proposed method. The proposed system in the figure described below includes the proposed BioGAT model for optimizing wireless sensor networks. We begin by strategically placing sensor nodes throughout a defined area, each with a specific initial energy level. The nodes are randomly positioned to ensure complete coverage of area. Energy consumption during operation is determined by the distance between the nodes and the type of transmission, with a different energy cost for transmitting and receiving data. The model uses biogeography-based optimization to select the most efficient cluster head, with the goal of balancing energy use across the network while maintaining effective coverage. This figure describes initial setup and parameters in the pre-processing stage, and then node deployment after energy model and proposed BioGAT model. This will be the two-step phases called BBO and GAT. BBO arbitrary index and the cluster head selection. After that, geographically attained GAT, attention coefficients and dynamic topology optimization. Later in the end process, energy consumption and update, network performance metrics, end of life and network sustainability statistical analysis. And proposed BioGate model is begin the optimization process, later input wireless sensor network topology, macro level optimization BBO, micro level optimization CATs, and later optimization loop, and finalize the optimized wireless sensor networks configuration. The results and analysis describes the simulation parameters for our wireless sensor network model are presented in the below table. The parameters comprises the field's dimensions, which are configured to be 100 meters by 100 meters, setting the probability of data transmission by a node to zero point 0.1. Each node possesses an initial energy of zero point 0.5 joules. Operating the transmitter or receiver requires 10 by 10 power minus 9 joules of energy per bit. Additional parameters include the data aggregation level, the energy amplifier coefficient for free space and multipath models, the number of sensor nodes, the number of mobile nodes, the sync coordinates, the initial number of dead nodes, and the threshold energy required for a node to attain the leadership position. The comparison of various network parameters for different rounds for 100 nodes. Lifetime 50 rounds 443.21, later 750 rounds 471, and 1000 rounds 621.21. Average throughput 141, 138, 140. Average end-to-end delay 0.38, 0.41, 0.44. Packet delivery ratio 0.94, 0.95, and 0.94.9. And the figure describes shows an average consumption energy consumption plot that compares the performance of various algorithms over a range of 100 to 300 nodes with the BioGAT, the proposed method the highlighted in purple. Numerically, BioGAT outperforms the other methods by maintaining the lowest average energy consumption as the number of node grows. Average end-to-end delay comparison. The purple one describes the BioGAT model. Conclusion and the future scope of my work. The creation and assessment of BioGAT model signify a sustainable progression in the optimization of wireless sensor networks by employing graph attention networks and biogeography-based optimization. The model successfully tackles a significant obstacles including node placement, energy efficiency, and network dependability. The integration of cluster heads for the purpose of data aggregation results in enhanced energy efficiency and an extended lifespan of network. The superior performance of the BioGAT model is evidenced by its extensive simulation results, which reveals a remarkable 95% packet delivery ratio and increased throughput in comparison to earlier approaches. Furthermore, the model demonstrates a significant decrease in mean energy consumption, thereby highlighting its capability to improve the sustainability and dependability of networks in a wide range of wireless sensor network applications. Subsequently, investigations might center on enhancing the BioGAT model's capacity by accommodate fluctuating environmental circumstances and expand to accommodate more extensive network deployments. Furthermore, conducting an inquiry into the model's operational implementation and deployment in tangible situations would yield significant knowledge regarding its efficiency and suitability. In general, the BioGAT model exhibits potential in furthering the functionalities of wireless sensor networks and enabling their extensive implementation across diverse domains. Further research can investigate several important avenues to further deployment the findings of a BioGAT model, validating the performance of the model across diverse wireless sensor network applications can be achieved by testing in larger and more complex networks, thereby expanding its scalability. These are the references that helps me to prepare this paper. Thank you for giving me this opportunity.